In the previous lesson, we discussed probability theory, but we didn't spend much time with difficult calculations. Instead, our interest was in how to think clearly about chancy situations. In this lesson, we'll continue with that theme by considering situations that are a bit more complicated than what we've already seen. Our main tool for doing that will be the infamous Monty Hall problem, also known as the game show problem and the three doors problem. Now, if you've never heard of the Monty Hall problem, then you're really in for a treat, since it's one of the all-time classics of mathematical brain teasers. But the problem is so famous that there's a good chance you've heard it before. If you have, though, I urge you to stick around anyway, since I think I can show you a few angles you probably haven't seen. The Monty Hall problem is based on the format of a 1970s game show called Let's Make a Deal. The host of the show was named Monty Hall, hence the name of the problem. The problem goes like this. You're on a game show, and the host shows you three identical doors. He tells you that behind one of the doors is a car, and that behind the other two are goats. Of course, we'll assume that you want to win the car. The host asks you to point to one of the doors, and you do so. You don't open the door, you just point to it. The host, who knows where the car is, now opens one of the other two doors and reveals a goat. Now, notice that if your choice actually conceals the car, then Monty could open either of the two doors, so we'll assume that he mentally flips a coin to decide which one to reveal. He now gives you two choices. You can either stick with your original choice, or you can switch to the other door. You make your choice, and then you win whatever is behind the door you've chosen. The question is this: what choice should you make to maximize your chances of winning the car? Should you stick with your first choice, switch to the other door, or does it not make a difference? Now, if you've never seen this before, I definitely recommend pausing the video for a moment to think it over. What would you do if you were actually in this situation? At first glance, this doesn't seem to be a difficult puzzle at all. We could argue that after Monty opens a door, there are really just two doors left in play. These doors are equally likely to conceal the car, so it's just another 50-50 situation. So what difference does it make whether you stick or switch? So simple. Such an obvious answer. But we've been burned by obvious answers before. And if the problem were really so simple, then it would never have become a classic. It turns out that the correct answer is to switch when given the opportunity, because you actually double your chances of winning by doing so. You heard that right. You double your chances of winning by switching to the door you didn't originally pick. So how do we arrive at this remarkable answer? Well, there are actually a couple of ways. The simplest is to actually play the game over and over again, keeping track of how many times you win by switching and how many times you win by sticking. You can find simulations of the game on the internet, and if you play the game repeatedly, you'll quickly find that you win much more often by switching than by sticking. You can also play with a friend using a deck of cards. You can use the ace of spades, say, to represent the car, and the two red kings to represent the goats. Then one of you can play the host, the other plays the contestant, and let the fun commence. Playing the game is good for convincing yourself that the 50-50 solution is not correct, but it does little to shed light on why switching is the correct strategy. So how do we think clearly about what's really going on here? What does the 50-50 argument overlook? We'll come to that point momentarily. But first, it's worth considering what can be said on behalf of the other options. For example, it turns out that most people, when actually confronted with the Monty Hall scenario, actually opt to stick with their original choice. Their argument is usually that if you switch and lose, then you'll feel like such a chump that it's better just to stick with your original choice. This reflects a fact of human psychology that's well known to cognitive scientists. If you take an action that incurs a loss, you feel worse than you would have if you suffered the same loss because of inaction. For example, let's say someone buys a stock that goes down in value by $10. Someone else decides not to buy a stock that then goes up in value by $10. Both people lost $10, but the first person tends to feel worse. He thinks, I brought this on myself, while the second person thinks, oh well, I just got unlucky. And so it is with the Monty Hall scenario. Mathematically, though, I think we're justified in ignoring this argument. The problem is to maximize our chances of winning the car, not to minimize our chances of feeling like a chump. So how about switching? Well, we could argue that your first choice conceals the car 1/3 of the time. That means that 2/3 of the time, the car is behind one of the other two doors. That doesn't change just because Monty opens a door that he knows conceals a goat. And that's why you double your chances of winning, from 1/3 to 2/3, by switching doors. That last argument is pretty good, actually, and the conclusion is correct. But even this argument overlooks a subtle point, and I'm not sure if it really gets to the heart of why people find this problem so confusing. So let's try to think clearly about the Monty Hall scenario. Why exactly is the 50-50 argument wrong? Well, it's wrong because it's based on the idea that when Monty opens a door, the only thing you've learned is that that door conceals a goat. Let's make this more precise. Suppose that the player initially chooses door 1, and then Monty opens door 2 to show a goat. Many players respond by thinking, I now know that the car is not behind door 2, but I've learned nothing about the other two doors. But this is an error. What the player should think is, by the rules of the game, Monty is not allowed to open my door, and he's not allowed to open the door with the car. Yet he chose to open door 2 anyway. He's far more likely to make that decision when the car is behind door 3 than when the car is behind door 1. Therefore, I should now think that the car is probably behind door 3, so I will switch doors. Why do I say that? Well, keep in mind that I'm pointing at door 1. If the car is actually behind door 3, then the rules of the game force Monty to choose door 2. But if the car is actually behind door 1, which I chose, then Monty can open either of the other two doors. And we know that he now flips a mental coin to decide which door to open. So he'll only open door 2 half the time. And this is the crux of the matter. So let's reiterate the main point. I've chosen door 1. If the car is behind door 3, then it's a sure thing that Monty will open door 2. But if the car is behind door 1, then it's 50-50 that Monty will open door 2. That means that when I see Monty open door 2, I should think, I have just witnessed an event that's twice as likely to occur when the car is behind door 3 than when the car is behind door 1. So I should definitely switch to door 3. To see if we have the hang of this, let's mix things up a bit. Let's refer to the Monty Hall we've seen to this point as Classic Monty. But suppose we have a different host, who we'll call Random Monty. Random Monty does things a bit differently from Classic Monty. You see, Random Monty doesn't know which door conceals the car. He's afraid his body language might reveal clues about where the car is, so he prefers not to know. When Random Monty is hosting the show, the game plays out a bit differently. The player chooses a door, but then Monty just opens one of the other two doors at random. Maybe it reveals a goat, and maybe it reveals a car. If it reveals the car, then the game ends right there, and the player just walks away with nothing. So let's say we're playing with Random Monty as the host. You start by choosing door 1, and then Random Monty opens door 2. You see that it conceals a goat. Once again, you're given the option of switching. Should you? See if you can apply the sort of reasoning we used with Classic Monty to decide what you should do here. Pause the video here to have a go at this yourself. Okay, let's see what we can make of this situation. We chose door 1, and then Random Monty threw open door 2 and just happened to reveal a goat. Now, if the car is actually behind door 1, then it's 50-50 that Monty will open door 2 since he chooses his door randomly. But if the car is actually behind door 3, then it's still 50-50 that Monty will open door 2. Remember that Random Monty doesn't know where the car is. He still won't open your door. But other than that, it's always 50-50 between the other two doors. So what should the player do? The player should think, I have just witnessed something that is equally likely to occur regardless of whether the car is behind door 1 or door 3. So in this case, it's true that I've only learned that door 2 conceals a goat, but that I've learned nothing about the other 2 doors. This time, the 50-50 argument is actually correct. It makes no difference whether I stick or switch. Maybe this result seems counterintuitive. After all, even with random Monty, your first choice is only right 1/3 of the time. But according to our analysis, after we see random Monty open door 2, we suddenly think our door is right half the time. Are we really saying that the probability of our door goes up when we see Monty open his door? Well, yes, that's what we're saying. Let's assign some numbers to this. Suppose we play classic Monty 30 times, and that we switch every time. Then our initial choice will be correct 10 times out of those 30, and that means we'll win 20 times and lose 10 times on average. But now suppose we play random Monty 30 times. Then in 10 of those 30 games, the door Monty opens will actually reveal the car, and the game ends right there. So when we stipulate that Monty reveals a goat, we're saying that we're not in one of those 10 games. And that's why the probability of our door changes. In the remaining 20 games, the car will be behind door 1 10 times and behind door 3 10 times on average. So it really is 50-50. And now we can also flesh out what I meant when I said that the argument for switching, that Monty can't change the 1/3 probability that our initial door was correct, was overlooking something. Random Monty shows that actually Monty's actions can change that initial 1/3 probability. What matters is the precise method he uses for choosing his door. That's precisely why we were careful to stipulate that classic Monty mentally flips a coin when he has a choice of doors to open. We can see an extreme example of this by considering yet another host. Let's call him 3-obsessed Monty. He makes decisions differently from either classic Monty or random Monty. Like classic Monty, he knows where the car is and will never open the door that conceals it. He also will never open the door you chose. But in addition, he holds to one other rule. He'll always open door 3 when he can do so without violating the other 2 rules. You can assume that if the player starts by choosing door 3, then 3-obsessed Monty will behave exactly like classic Monty. So, this time, you know that 3-obsessed Monty is hosting the show. You chose door 1. If Monty now opens door 2, then what would you conclude? And what would you conclude if Monty opens door 3? You should pause the video here if you want to think that over. Did you get it? Let's suppose Monty opens door 2. You should now think, wait a second. Why didn't Monty open door 3? He's 3-obsessed, after all. He would have opened door 3 had he been able to do so without violating his other rules. He can't open my door, but since I chose door 1, that's not an issue. The only other rule is that he won't open the door with the car. So it must be that he didn't open door 3 because the car is behind it. That means I win for sure if I switch doors. And if Monty opens door 3 instead? Now we would think he opened door 3. No surprise there, he's 3-obsessed after all. But he would have opened door 3 regardless of whether the car is behind door 1 or door 2. So in this case, it's 50-50 again, and it doesn't matter what I do. But either way, you should no longer think that your initial choice is only correct 1/3 of the time. I hope that clarifies some of the issues involved in thinking clearly about probability. It all takes some getting used to. Even for mathematicians and statisticians, it can often be difficult to work out these problems carefully. The Monty Hall problem is famous precisely because so many people have gotten it wrong over the years. In 1975, an academic journal called The American Statistician published a letter to the editor discussing the problem. To be clear, this is the sort of journal that's read primarily by professional statisticians. The author of the letter presented the correct solution, namely that you should switch. The journal was subsequently deluged with outraged responses claiming that the 50-50 solution was actually correct. This story repeated itself in the pages of Parade magazine in 1990. They ran a column by Marilyn Vos Savant in which she answered questions sent in by readers. These questions often involved math and science. One day, a reader sent in the Monty Hall problem, and Vos Savant answered correctly that you should switch. The magazine was swamped with angry letters, many of them by mathematicians, arguing that it makes no difference whether or not you switch. Probability is very counterintuitive, even for people with training in this subject. This is why one prominent cognitive scientist said of the Monty Hall problem, "No other statistical puzzle comes so close to fooling all the people all the time." The phenomenon is particularly interesting precisely because of its specificity, its reproducibility, and its immunity to higher education. But now let's switch gears a little bit. To this point, I've been stressing the value of thinking clearly about probability. We haven't calculated very much, and I've been avoiding using equations and jargon. But sometimes those equations and jargon actually help to clarify things. So let's have a go. When you first see probability, it's really little more than just counting. When you flip a coin, there are two possibilities, and only one of them is heads, so the probability of flipping heads is 1 out of 2. When you pick a card out of a deck, there are 13 hearts out of 52 cards, so the probability of picking a heart is 13 out of 52, which is the same as 1 out of 4. The total number of possibilities goes on the bottom. The number of possibilities that match whatever you're interested in goes on top. Nothing to it. But the Monty Hall problem presents us with something different. We're no longer trying to calculate a probability by itself. Instead, we want the probability of some event given that some other event has already occurred. Specifically, we're asking for the probability that our initial door was correct, given that we've just seen Monty Hall open one of the other doors. Mathematicians call this conditional probability. Here's a simple example. If we draw one card from a deck, we've just seen that the probability of getting a heart is 1/4. But now suppose I tell you that the chosen card was red. What's the probability that the card is a heart, given that we know that it was a red card? That's a different question from before, though still not very difficult. We know there are 26 red cards and that 13 of them are hearts. So the probability is now 13 out of 26, which is 1/2. But the Monty Hall problem does not seem to be a simple matter of counting. Different scenarios, where's the car? Why did Monty do what he did? Play out with different probabilities. So we need a more formidable weapon if we're going to assign some numbers to what's going on. The tool that mathematicians use for problems of this sort is called Bayes' theorem, after an 18th century scholar named Thomas Bayes. If you open a textbook on probability theory, and who hasn't, and look up Bayes' theorem, you'll find this equation. That might look like alphabet soup, but let's see if we can understand what it says. Remember that equations are just sentences. It's important to try to understand what they're really saying. In this equation, A and B represent events that might occur. The term on the left is the probability that A will occur given that B has already occurred. The equation tells us that this probability depends on 3 things. First, it depends on how likely you thought A was to begin with. That's the P of A term on the right. It also depends on how likely B is on the assumption that A has occurred. That's the probability of B given A term. And finally, on the bottom, we have the probability of B by itself, and that's the P of B term. Now, that might still look like alphabet soup. So let's see what this means in a practical situation. Suppose you're a detective investigating a murder. You discover that the suspect's fingerprints were found at the scene of the crime. Is this good evidence for the suspect's guilt? What's the probability that the suspect is guilty given that his fingerprints were found at the scene? Well, a good piece of evidence is one that's very likely to be found if the suspect is guilty. In this case, if the suspect really is guilty, then we'd expect to find his fingerprints at the scene. So far, so good. But that can't be the end of the story. A defense attorney might argue that there's a perfectly innocent explanation for why the suspect's fingerprints were found at the scene. Maybe the crime occurred at a place that the suspect routinely visits for entirely innocent reasons. If that's true, then the value of the fingerprints as evidence goes way down. So, a good piece of evidence is one that's very likely if the suspect is guilty and very unlikely otherwise. And that's really what Bayes' theorem is saying. How likely is A given B? Well, if B is very likely given A, then the probability of A goes up, so that term goes on top. But if B is very likely regardless of whether or not A is true, then its value as evidence for A goes down. So that term goes on the bottom. Remember, with fractions, a big number on the bottom makes the fraction smaller. That's the reasoning behind Bayes' theorem. Let's see how it applies to the Monty Hall problem. Let's start with classic Monty. We'll say that A is the event that the car is behind the door you chose first, and let's say that B is the event that Monty opens some other door to reveal a goat. We want the probability of A given B. Bayes' theorem says this probability depends on three things. First, we need the probability that the car is behind my initial door, and that probability is 1/3. Second, we need the probability that Monty will open a door to reveal a goat under the assumption that the car is behind your chosen door. That probability is 1, since Monty will never open the door you initially chose. And third, we need the probability that Monty will open a door to reveal a goat. This probability is also 1, since Monty will never open the door that conceals the car. When we plug everything into Bayes' theorem, we get 1/3 times 1 on top, which is 1/3, and on the bottom, we just get 1. So the answer is 1/3 over 1, which is 1/3. In other words, with classic Monty, the probability that your door is correct after Monty opens his door is the same 1/3 you thought it was before Monty did anything. And if we try this for random Monty, well, the numbers on top haven't changed. Your initial door is still correct 1/3 of the time. If the car is actually behind your initial choice, then Monty definitely won't reveal the car. But the number on the bottom has changed. Random Monty sometimes reveals the car. Specifically, he'll randomly choose a door, and that door will conceal the car 1/3 of the time. So the probability that he opens a door to reveal a goat is now just 2/3 and not 1 like it was before. So Bayes' theorem says that the probability that our initial door was correct, given that Monty showed a goat, is now 1/3 times 1 on top, divided by 2/3 on the bottom, and that works out to be 1/2, just as we calculated before. It would seem that the equations confirm our intuitions. Okay, are you ready for the final exam? We'll call this one Mystery Monty. Here we go. Suppose that classic Monty and random Monty are both backstage. They flip a coin to decide who will host the show. You don't know which host you got. You choose door 1, and Mystery Monty opens door 2 to reveal a goat. Should you switch? If you want to have a go at this, then pause the video here. Of course, we could argue that if we got classic Monty, then we should definitely switch. And if we got random Monty, then it doesn't hurt us to switch, so we might as well switch. That's a very decent argument, but we're looking for something a bit more specific. We want to know what the probability is that we'll win by switching. So let's see if we can combine our intuition with some calculations to get that answer. This gets a little tricky, but I think we can get through it. The key observation is that when Mystery Monty opens door 2 to reveal a goat, you get some information about which host you've actually gotten. What's the probability that classic Monty opens door 2 to reveal a goat? Well, there are 2 possible scenarios, keeping in mind that you chose door 1. It could be that the car is behind door 3, and then Monty is forced to open door 2. And since the car is behind door 3 1/3 of the time, this scenario has probability 1/3. Or it could be that the car is behind door 1, and then a mental coin toss led to Monty choosing door 2. This scenario has probability 1/3 times 1/2, which is 1/6. Since these scenarios are independent of one another, we can just add the probabilities to get 1/6 plus 1/3, which is 1/2. So when you choose door 1, classic Monty opens door 2 and shows a goat half the time. How about random Monty? When you choose door 1, random Monty will open door 2 half the time. It will conceal a goat 2/3 of the time. So this scenario plays out with probability 1/2 times 2/3, which is 1/3. When we see Monty open door 2 to reveal a goat, we should think this event happens with probability 1/2 with classic Monty and with probability 1/3 with random Monty. So it's more likely that my host is classic Monty. More specifically, it's 3/2 more likely that I got classic Monty than that I got random Monty, because 3/2 times 1/3 is 1/2. This tells me that I got classic Monty with probability 3/5 and that I got random Monty with probability 2/5. Notice that 3/5 divided by 2/5 is 3/2. Now, with classic Monty, I win by switching 2/3 of the time, and with random Monty, I win by switching half the time. So with mystery Monty, the probability that I win by switching will be the weighted average of these probabilities, and that's 3/5 times 2/3 plus 2/5 times 1/2. That's equal to 2/5 plus 1/5, which is 3/5. So with mystery Monty, I'll win by switching 3/5 of the time. A very nice result. Believe it or not, this is really just the tip of the iceberg. I think you could literally teach an entire college course in probability theory using nothing other than variations on the Monty Hall problem. But I think that's enough for today. See you next time.